The night sky looks peaceful. It looks still, but that's an illusion. Up close, the universe is violent. It's chaotic. And that's the contradiction. The smooth cosmos we see, and the frantic reality we know is there. That's one of the big mysteries now. The laws that force the universe to have these two faces. We'll get to those. There's an ancient snapshot of light that's the key. And the empty spaces between galaxies matter just as much as the galaxies. So this cosmic duality, what it shows about the true nature of reality. You picture a pointillist painting. From far away, it's a calm landscape, a river, soft hills, but you move closer. That smooth scene breaks apart into individual dots, just dabs of pure color, chaotic up close, no real order. Then you step back again, and the chaos blends, it resolves. Your eye averages it out, turns noise into a picture. That's more than art. It's the perfect analogy for how we see the cosmos. The universe is that canvas, and the main tool we use to see it, the thing that turns chaos into calm, is scale. Our perception is stuck in a narrow band. We're built to see trees, not forests, to feel the wind, not the whole climate pattern. When we look up, our eyes, even our biggest telescopes, they're taking a step back from that cosmic canvas. From that huge distance, the frantic dots, individual solar systems, colliding galaxies, exploding stars, they all blend together. They average out into a serene, almost featureless backdrop. That was one of the big realizations in early modern cosmology. Astronomers like Edwin Hubble, he mapped galaxy positions. He found something. If you zoom out far enough, take a wide enough view, the distribution of these island universes becomes remarkably even. It's like a vast, three-dimensional foam. The bubbles are galaxy clusters, and the structure looks roughly the same in every direction. That large-scale uniformity is what we call smooth. But it's crucial to understand this smoothness isn't a physical substance. It's a statistical reality. It comes from counting. Imagine a bag with 1,000,000 marbles. Half black, half white, all shaken together in a jumble. Grab 10 marbles. You might get 7 black, 3 white. That's lumpy. That's chaotic. But if you could grab 100,000 marbles at once, the ratio would almost certainly be very close to 50-50. The individual irregularities cancel each other out. The universe works on that principle, but at a scale so vast it defies intuition. What we see as the smooth, homogeneous cosmos is just the universe taking its own average. Over volumes of space so enormous that every cataclysm, every vast empty void, is just another marble in the statistical mix. That forces a question. If we had a God's eye view, infinite resolution, could see every atom in every star across the whole cosmos at once, would the universe ever look smooth? Or would it be nothing but a frenetic, seething storm at every scale? The answer seems to be that true smoothness is an illusion of limited perspective. It's a product of the lens we're forced to use. To understand how this averaging effect isn't just an observation, but something woven into the fabric of reality, we have to turn to the oldest snapshot in existence. There's a statistical principle called the law of large numbers. You flip a coin once, it's pure chance. A dozen flips, you might get something strange like 8 heads. But flip it 1,000,000 times, the result will be almost exactly half and half. All that individual randomness gets swallowed up. It just averages out. And the universe runs on this on the grandest scales. After the Big Bang, the distribution of matter wasn't perfectly even. There were tiny, random quantum fluctuations. But when you look at a volume of space containing hundreds of thousands of galaxies, those fluctuations cancel each other out. The dense spots and the empty voids together, they produce a statistical smoothness. That's why cosmologists like George Smoot, when they studied the cosmic microwave background, that ancient light from the universe's infancy, they found something. That afterglow is nearly perfectly uniform. The temperature differences across the whole sky are minuscule, variations of only about 1 part in 100,000. It's the ultimate example of large-scale averaging in nature. The cosmos ran the ultimate probability experiment. Over a volume that vast, the law of large numbers enforced an order. And from our distant viewpoint, that order looks like serenity, but this creates a disconnect. We live and observe within the chaos, not from outside it. It's the difference between surveying a forest from a plane and being lost in the middle of it. From above, the canopy is just an unbroken green sea. But on the ground, your reality is the specific tree in front of you, the clearing to your left, the thicket you can't get through. The overall average means nothing to your immediate experience. So what does that mean for finding cosmic truth? If the fundamental laws of statistics are actively painting over the universe's rough details to give us a smooth facade, what else are we missing? What other realities are hidden because we can't step far enough back to see the whole picture at once? From orbit, the Earth looks like a perfect blue marble. Serene, unblemished. From that height, a hurricane is just an elegant white swirl. A mountain range is a subtle wrinkle. The chaos of a thunderstorm, the violence of an earthquake, the sprawling light of a city at night, all of it gets smoothed into a single, tranquil sphere. That's the power of a vantage point, and it's the second principle that shapes how we see the cosmos. We aren't astronauts looking down. We're creatures standing on the ground, looking up from one fixed point in a vast arena. Our observation isn't just distant, it's profoundly local. We see everything from one tiny speck at one specific moment in a 13.8 billion year history. And that vantage point imposes a filter on reality. The most fundamental filter is time, delivered by the finite speed of light. You look at the sun and you see it as it was about 8 minutes ago. You look at the Andromeda galaxy and your eyes receive light that began its journey 2.5 million years ago. You're seeing a younger universe, a historical artifact, and as you peer deeper into space, you peer further back in time. The most distant galaxies we can detect appear as they were when the cosmos was just a fraction of its current age. They were simpler systems, often smaller, more uniform. The complex, chaotic dance of mature galaxies we see nearby hasn't had time to develop in that distant view. So the farther out we look, the smoother the universe appears, more primitive, not necessarily because it was perfectly smooth then, but because we're seeing its childhood portrait before all the detailed wrinkles of age had formed. This time delay combines with another effect, described by astronomers using tools like the Hubble Space Telescope. It's called cosmological redshift. As the universe expands, it stretches the very wavelengths of light traveling through it. Light from extremely distant objects gets stretched so much it becomes redder. And fainter, fine details, the sharp edges of cosmic chaos, get washed out over these epic journeys. It's like trying to hear a symphony from miles away. You might catch the melody, the broad sweep of the music, but all the individual notes, the clash of cymbals, the nuance of a single violin are lost. They're filtered out by the distance. The universe's expansion acts as that filter, subtly smoothing the signal we receive. Then there's the sheer scale of time. A massive star might live for only 10 million years before exploding in a supernova. That's an eternity to us, but in cosmic terms, it's a brief, brilliant flash. These chaotic events are like fireworks in a dark sky. From our distant viewpoint, we don't see the momentary, violent explosion in detail. We see its contribution to the overall, steady glow of the galactic city. These processes are localized, they're fleeting, they are the cosmic noise, and over the span of light years and eons, that noise averages out. What persists, what defines the large-scale structure, is the underlying pattern. The gravitational scaffolding that took billions of years to assemble, our limited vantage point, bound by the speed of light and our singular location, naturally emphasizes that enduring structure and mutes the temporary chaos. So the serene universe we map isn't a lie. It's a true picture, but a specific one. It's the picture you get by listening only to the deepest, longest-lasting notes of the cosmic symphony. To understand why that symphony sounds so harmonious in the first place, you need the one instrument that can hear its opening chord. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna. They kept hearing this noise, a constant hiss. It was coming from every direction in the sky, and it wouldn't stop. They checked everything. They even cleaned out pigeons that had nested in the antenna. But the hum was still there. It wasn't a glitch. They had found the cosmic microwave background, the oldest light in the universe. After 13.8 billion years of expansion, it had cooled down to just a whisper in the microwave spectrum. This was the evidence for the Big Bang, and it showed something simple. The early universe was a hot, opaque soup of particles and radiation, and this first picture showed it was almost perfectly smooth. The temperature was the same everywhere, to within about 1 part in 100,000. George Smoot, who mapped this background, called it seeing the face of God. It was the large-scale average, the starting condition for everything. Later missions like WMAP and Planck mapped this afterglow in detail. Their maps show a mottled oval, a cosmic fingerprint in blues and reds for those tiny temperature differences. But the overall picture is one of uniformity. This isotropy means the early universe was a remarkably homogeneous plasma. But those tiny fluctuations, the 1 part in 100,000 variations, they are everything. They are the seeds. The slightly denser patches in that early fog had a small gravitational pull. Over billions of years, they attracted more matter. They grew into the first stars, the first galaxies, the great clusters, and the vast voids we see now. All the structure of the modern cosmos, the whirlpools of galaxies and the empty spaces, were written into that smooth snapshot as tiny ripples. So how did the universe get into this state, smooth overall, but imprinted with the pattern for all future complexity? The leading idea is called inflation. In the first fraction of a second after the Big Bang, the universe is thought to have gone through a period of hyper-fast expansion. It grew by an unimaginable factor in an instant. This process did two things. First, it took any primordial irregularities and stretched them out so much that the observable universe became incredibly uniform. Think of the surface of a balloon. Uninflated, it's wrinkled. But when you blow it up, the surface becomes smooth. Inflation was the breath that smoothed the wrinkles of the infant cosmos. But second, and more importantly, inflation didn't create perfect smoothness. It took the inherent quantum jitter, the tiny fluctuations that exist even in a vacuum, and stretched those to cosmic size. So the smoothness we see in the cosmic microwave background isn't a blank slate. It's a canvas that's been ironed flat, but the faintest texture, the quantum grain of reality itself, has been imprinted and magnified. Under extreme magnification, that smooth balloon surface shows its rubbery texture. The Planck satellite's map is that extreme magnification. Those small splotches are the quantum fingerprints, inflated to become the blueprints for galaxies. So the cosmic microwave background shows both sides. From our distant view, it looks like a serene, uniform glow, the definition of cosmic smoothness. But encoded in that serenity, in its faint temperature differences, is the detailed, chaotic destiny of everything to come. It's the universe showing us both faces at once. That ancient light shows a cosmos that was perfectly smooth, a serene, uniform pond of energy, but we live in a universe of whirlpools and islands. So how did we get from that placid beginning to this cluttered present? The answer is in the tiniest of seeds. those minute temperature differences in the cosmic background radiation, the 1 part in 100,000 variations. Those weren't imperfections, they were the blueprint. Think of that smooth pond again, and imagine dropping a handful of the finest sand into it. Each grain creates a tiny ripple. At first, the pond seems unchanged, but as time passes, those ripples begin to cross. They interfere, they amplify in some places, they cancel out in others. A complex pattern emerges from a simple start. The early universe was that pond, and the quantum fluctuations stretched by inflation were those grains of sand. The ripples were in density, microscopic patches of space that were slightly more packed with matter, ever so slightly. This is where the true architect of cosmic chaos takes the stage. Gravity, it's the universe's great amplifier. A region with just a tiny bit more mass exerts a slightly stronger pull. It acts like a cosmic magnet, slowly drawing in matter from the less dense areas around it. As it grows denser, its pull strengthens. It attracts even more. Over millions of years, then billions, this snowball effect transforms a whisper of difference into a shout. A faint ripple becomes a mountain. Physicists like Jim Peebles helped map this story. They called it gravitational instability. It's the fundamental narrative of structure. We can watch this story play out in supercomputer simulations. They start with a nearly smooth universe, seeded with those tiny density fluctuations. Then they press play, letting gravity work over cosmic time, and you see a cosmic web begin to form, filaments of matter glowing like threads in the dark. Where the threads intersect, dense knots form. These are the proto-galaxies, the nurseries for the first stars. The spaces between the threads, the regions that started with slightly less matter, are emptied out by gravity's pull. They become the great cosmic voids, vast deserts of near-nothingness spanning hundreds of millions of light-years. From a nearly featureless fog, gravity sculpts a universe of complexity. Stark contrast, it makes you wonder, what if those initial seeds had been even smaller? If the early universe had been perfectly smooth, with not even those quantum ripples? Would gravity have had anything to work with? The likely answer is a profound and empty yes. Without those seeds, matter would have remained spread in a thin, uniform haze. No stars would have ignited, no galaxies would have spun, no planets, and certainly no us. Our existence hinges on that primordial imperfection. Gravity wrote the story of the cosmos, but it needed those first few words to begin. And while gravity built the visible framework, another, more mysterious force was shaping the empty space itself. Gravity needed a blueprint, and dark matter was the canvas. A pitch-black room, you can't see anything, but you can reach out, feel the shape of a table, the edge of a chair. You can map the whole layout without ever seeing it. Dark matter is the unseen furniture. It's the dominant form of matter, about 85% of all the mass, and it has one property: it doesn't interact with light. It doesn't emit it, absorb it, reflect it. It's completely dark, so we can't see it with any telescope. We only know it's there because of its gravity. Its pull on the things we can see, stars, galaxies, and this invisibility gives it a characteristic. On the largest scales, dark matter is smoother than ordinary matter. Because ordinary matter, baryonic matter, can do something dark matter can't. It can feel pressure, it can radiate heat, it can crash together, ignite into stars. Explode. These processes are violent, chaotic. They cause gas and stars to clump in uneven ways. Dark matter is aloof. It passes through itself and everything else. Like a ghost, it only feels gravity. So as the universe evolved, dark matter settled into vast, diffuse clouds, halos under its own gravity. These halos are enormous. Hundreds of thousands of light years, and from our distant view, their distribution looks smooth, even a cosmic skeleton, the true scaffolding. Supercomputer simulations show this. The Millennium Run, they model the universe starting with tiny primordial ripples. Let dark matter's gravity act over billions of years. What emerges isn't a random scatter. It's an intricate, three-dimensional web, a cosmic spiderweb, filaments of dark matter stretching across emptiness. Where the filaments intersect, you get dense knots. The halos, and it's within these invisible halos that the luminous universe is built. The ordinary matter, gas and dust, falls into these gravitational wells. It swirls, heats up, collides, forms stars and galaxies. So the bright galaxies we see are just froth on the surface of a deep, dark ocean. They trace the underlying structure, but they aren't the structure itself. It's a division of labor. Dark matter provides the smooth, large-scale framework. Baryonic matter provides the brilliant, clumpy details. Think of a great river from a mountaintop. Its course is a single, smooth curve. That's the dark matter. But if you stand on the bank, your reality is churning white water, swirling eddies, the violent crash against rocks. That's the ordinary matter, confined and shaped by the river's broader flow. And this leads to a question. How much of the cosmic smoothness we observe is not a trick of perspective, but a fundamental feature of the universe's dominant, unseen component? The serene backdrop of the cosmos may be the serene nature of dark matter itself. A single spiral galaxy hanging in the void. From a distance, it's a stately whirlpool, a pinwheel of light. It looks ordered. It looks like harmony, but you cross that distance. You enter its domain, and the serenity dissolves. Inside those sweeping arms, chaos is the engine. Vast clouds of gas and dust, light years across, they collapse under their own weight. They fragment, they become knots, stellar nurseries like the Orion Nebula. Astronomers call them frenetic cauldrons. Gravity's grip triggers a violent birth. Protostars ignite. Their fierce winds carve out cavities in the nebula. New stars flash to life in chains of thermonuclear fire. It's a continuous tumult. Explosive, the life of a star born there is bookended by violence. It begins in a turbulent collapse, and for the most massive, it ends in a cataclysm. A supernova, for weeks, it outshines its entire galaxy. In a final act, the star tears itself apart. It scatters its enriched guts across space. That debris holds the heavy elements. Carbon, oxygen, iron, the stuff of planets, the stuff of life. This chaos isn't a flaw. It's the essential forge. Without the fury of stellar nurseries, without the apocalyptic deaths of supernova, the universe is just hydrogen and helium. No rocks, no water, no chemistry complex enough to ask questions. But for all its ferocity, this chaos is microscopic. It's a temporary spark, set against the enduring ember of the galaxy itself. You have to consider the timescales. A supernova's flash is over in months. The turmoil of a stellar nursery plays out over a few million years, but the galaxy, that grand spiral, has been turning for over 10 billion years. It completes a single rotation every 250 million years. The chaotic events are like brief lightning strikes inside a slow, ancient weather pattern. They're contained, they're averaged out by the galaxy's immense scale, by its relentless rhythm. Think of a beehive on a quiet summer day. From your porch, it's a silent wooden box. A picture of stillness, but you press your ear to it. The hive thrums with a low roar. Inside, it's a universe of frantic purpose. Thousands of wings beat. Bees dance, larvae are fed, the queen lays her eggs. It's a contained frenzy, essential to the hive's survival. Yet from even a short distance away, all that complexity blends into a single, serene hum. The galaxy is that hive. Our solar system is a single bee, buzzing through a local drama, largely unaware that its entire furious neighborhood contributes to a distant impression of graceful calm. This microscale turbulence, so vital and so violent, it's the final piece. It completes the picture, a cosmos that is both serene and seething, but it forces a question. What are the forces, the fundamental laws, that allow these localized tempests to exist without tearing the grand design apart? What contains the chaos? Gravity shapes chaos, but it also creates this hidden order. You have two stars, a binary system. From far away, they look like one light, but up close you see the dance. Each one moves in an ellipse around their common center. Johannes Kepler wrote those laws centuries ago. The motion is predictable. You can know where they'll be 1,000 years from now. That's the paradox. Gravity causes violent collapse, explosive deaths, and it also writes this elegant, predictable choreography. It does it through orbits. The planets aren't falling into the sun, they're falling around it. Isaac Newton found that universal grammar, mathematical rules that turn chaotic possibilities into stable, repeating patterns. This gravitational harmony scales up, way up. A globular cluster has hundreds of thousands of stars, a dense swarm. Close up, the interactions are fiendishly complex. A perpetual game of stellar billiards, but given enough time, something happens. The cluster reaches a relaxation time. The individual chaotic motions, through countless gentle nudges, they average out. The cluster settles, it finds a statistical equilibrium. From afar, it's no longer a frantic swarm. It becomes a smooth, symmetrical sphere, a fuzzy jewel in the telescope. This principle of averaging governs the grandest structures. The Milky Way has over 100 billion stars. If you tracked each one, their paths would be a tangled web. But when you step back and measure the galaxy's rotation, you find an astonishing smoothness. The collective motion of billions of chaotic orbits blends into a single, coherent flow. The galaxy turns like a great wheel. Think of a busy highway from a helicopter. From that height, the traffic is a steady, flowing river, but from the roadside, it's a chaotic rush of individual cars. Speeding up, slowing down, changing lanes. The galactic smoothness is that helicopter view. It's the large-scale average of innumerable small-scale journeys. This gravitational choreography hints at something deeper. The orbits work because spacetime itself has a certain smooth, predictable geometry. The planets follow the curves in that geometry. So we see chaotic matter moving within space, but the framework of spacetime seems to be the ultimate source of order, a serene canvas for the chaotic paint. But what if that canvas isn't so serene? What if the smooth fabric of spacetime has a hidden, turbulent texture all its own? Einstein gave us a new language for gravity. Matter and energy tell spacetime how to curve, and then curved spacetime tells matter how to move. The equations are elegant. They describe the geometry of reality. But what do they tell us about the shape of the cosmos? The answer is strange and profound. On the largest scales we can measure, the universe is flat. Not flat like a table, flat in a geometric sense. The overall curvature of spacetime across everything we can see is nearly zero. That's a key finding from missions like Planck. It means if you drew a truly enormous triangle between three galaxy clusters, its angles would add up to 180 degrees. Parallel light beams stay parallel. The cosmic fabric, in the broadest view, has no overall bend. It's like standing on a prairie, stretching to the horizon in every direction. The ground feels flat because the curve of the Earth is too gentle to see right where you are. The cosmos is that prairie, but on a scale so vast it's almost impossible to conceive. This geometric flatness is a cornerstone of modern cosmology. It tells us something critical about the density of the universe. There's a precise, critical density required for flatness, and our measurements show the universe's total mass and energy match that value with astonishing precision. It's a delicate balance written into the cosmos from the beginning. Cosmologist Max Tegmark has noted this isn't a coincidence. It's a clue. A flat universe is one that can expand forever. Its geometry forever poised between eternal collapse and runaway dispersal. But this large-scale flatness is an average. A cosmic prairie still has rocks and gullies. Get close to a star, a planet, a black hole, and the fabric of spacetime is anything but flat. It's warped, twisted. These are the gravity wells. Imagine a vast, taut rubber sheet. That's the smooth, flat universe. Now place a heavy bowling ball in the center. The sheet dips sharply around it. That's the sun curving spacetime. Roll a marble nearby, and it spirals into the dip. That's a planet in orbit. Now imagine not one ball, but billions of all different weights. Some are so dense they punch holes right through the sheet, black holes. The sheet becomes a chaotic landscape, pits and slopes. This is local curvature. It's wildly variable. It's the source of the gravitational chaos we see up close. Yet, if you could step back, look at that entire sheet from a great distance, you'd see something remarkable. All those individual dips and wrinkles average out. The sheet as a whole still appears flat. The overall geometry hasn't changed. This is the universe's dual nature, written into the fabric of spacetime. The smooth, flat backdrop is real. The violent, curved topography is also real. They coexist, each true at its own scale. This geometric perspective forces a question. Is this large-scale flatness permanent, or just a phase in an epic cycle we cannot yet see? Spacetime's smooth geometry wasn't the end of the story. Around the turn of the millennium, something new was added. A shocking force. The universe's expansion isn't slowing down, it's accelerating. That finding was so unexpected it won the Nobel Prize. Teams were looking at distant supernova, these cosmic mile markers. They found the explosions were fainter than they should have been. The only explanation was that space itself was stretching faster and faster, pushing galaxies apart at an ever-increasing rate. They called the cause dark energy. It's the dominant thing in the cosmos now, about 68% of everything, and its main effect is to act as the ultimate cosmic homogenizer. Think of raisin bread rising. The raisins are the galaxies. The dough expands and the raisins move apart, but then imagine the loaf starts to rise faster. Faster and faster, the raisins aren't just moving apart, they're being flung away from each other. From any one raisin's view, all the others are receding more evenly. More smoothly, the local clusters are still there, but the overall distribution looks more uniform. Dark energy is that, the accelerating expansion of the cosmic loaf. It works against gravity's power to clump things on the very largest scales. Gravity builds the cities, dark energy spreads them out into an ever more dispersed suburb. And that leads to a forecast, a profound long-term one. If dark energy's push continues, the future is one of increasing isolation, increasing smoothness. Galaxies beyond our local group will eventually be pushed away so fast their light can never reach us. The cosmic web will stretch, it will thin, the universe will grow vast. Cold and profoundly smooth in its emptiness, that potential fate is sometimes called the Big Freeze, or in more extreme models, a Big Rip, where even galaxies and atoms are torn apart by the runaway expansion. But right now, in our local corner, the chaotic battles still rage. Within galaxy clusters, gravity is still king. Galaxies whip past each other, they merge. They tear gas from one another in violent interactions. It's like watching an outgoing tide. From a high cliff, you see the tide receding, smoothing the wet sand into a vast, flat plain. That's dark energy's large-scale effect. But down on the beach, children are still digging chaotic pits, building elaborate sandcastles. Those are the galaxies. Governed by gravity's local rules, both realities are true at once. The accelerating tide is rising, even as we build our temporary structures in the sand. This duality forces a view. The cosmos isn't a single state, it's a dynamic tension, a battle between two fundamental influences, one that builds intricate, chaotic complexity. and another that, over eons, works to erase it, leaving behind a serene and silent expanse. This evolutionary view adds a new dimension to the duality. It's not just smooth here and chaotic there. It was smooth then, it's chaotic now, and it may become smooth again. A story in 3 acts. We're living in the brief, messy middle. The opening act was written by inflation, that hyper-fast expansion in the first fraction of a second. It ironed the cosmos into a state of near-perfect uniformity. A hot, dense plasma, which we see as the cosmic microwave background, that was the primordial smoothness. The stage was set, blank and featureless, save for the faintest quantum imprints. Then the second act began. Gravity took the lead. For billions of years it worked on those tiny seeds. It sculpted the first stars from the cooling hydrogen fog. It gathered them into proto-galaxies. It orchestrated collisions and mergers, building the great spirals and ellipticals we see. It spun the cosmic web with its brilliant filaments and cavernous voids. This is the era of structure formation, the age of increasing lumpiness. It's the act we find ourselves in, a golden age of cosmic architecture where chaos and complexity are the engines of creation. All the vibrant, violent, beautiful phenomena we observe, stellar nurseries, colliding galaxies, quasars, they're the signature of this middle chapter. But the script, according to our best models, has a third act, and the protagonist shifts to dark energy. As the universe's expansion accelerates, its large-scale geometry begins to reassert a different kind of order. Not the smoothness of a hot, dense beginning, but the smoothness of an immense, cold, and empty end. Galaxies beyond our immediate gravitational family will be carried away by the stretching space between us. Their light, already redshifted to a whisper, will eventually fade from view entirely. The cosmic web will stretch and thin. The brilliant knots of galaxy clusters will become isolated islands in an ever-darkening sea. For any civilization within such a cluster, the observable universe will shrink dramatically. The night sky, which for us is a tapestry of distant suns, will for them become a much darker place. The distant galaxies will have vanished over the horizon of space. All that will remain is the smooth, black backdrop of an expanding void, punctuated only by the few aging stars of their own lonely galaxy. This timeline forces a profound perspective. The universe's appearance isn't just a matter of where you look, but when. An observer in the first few 100 million years would have seen a smooth, glowing fog. We, observing now, see a universe rich with structure. An observer in 1 trillion years might see only a profound and empty stillness. Our entire understanding of cosmology, built on the light from distant galaxies, is only possible because we live in this specific, fleeting epoch when the lights are still on and visible to each other. It's a privileged moment in cosmic history. This leads to a haunting thought experiment. If a civilization did arise in that far future, with no knowledge of a clumpy universe, what would their science be? They would look out and see only their own galaxy, adrift in a perfectly smooth, dark expanse. They might conclude quite reasonably that their island is all that exists. The evidence for a Big Bang, for an expanding universe filled with structure, would have literally disappeared over the horizon. The history of the cosmos would be lost to them, erased by the very expansion that defines its fate. Our current view, then, is a temporary window, a glimpse of the universe in its vibrant, structured prime, caught between 2 eras of smoothness. The cosmos we see is really just old postcards. We're not seeing the universe as it is, but as it was, and that messenger light carries a story that's been edited by its journey. A quasar's beam might have started out when Earth was just barren rock. Over billions of years, it travels through an evolving cosmos, and that passage smooths its story. The first filter is simple dilution. Light spreads out from its source so it gets fainter. For something like a galaxy, that leads to surface brightness dimming. A distant galaxy's total light drops, but so does its apparent size. The result is the light is spread more thinly across our detectors. Fine details, the sharp edges of spiral arms, knots of star formation, they all fade. The galaxy becomes a featureless, soft glow. It's like looking at a distant city through thick evening fog. You see a uniform, hazy light. You know intellectually that glow is made of millions of individual streetlights, windows, headlights, but your eye can't resolve them. The fog acts as a homogenizing filter, turning sharp contrasts into a smooth, luminous blanket. That's what happens across cosmic distances. The void itself is that fog, smoothing the sharp features of the universe into the serene backdrop we map. But the journey involves more than just fading. Space isn't empty. It contains the warped geometry of gravity wells, and that leads to one of the most visually chaotic phenomena: gravitational lensing. When light from a distant galaxy passes near a massive foreground cluster, space-time curvature acts like a lens. It bends the light's path. The result can be dramatic arcs, multiple images of the same galaxy, even perfect Einstein rings. To a distant observer, it looks like chaos, a single galaxy smeared and duplicated. It breaks our intuitive map of the sky. Yet, for all that apparent disorder, gravitational lensing obeys the precise rules of general relativity. The chaos is an illusion of perspective, and when cosmologists look at the sky statistically, these dramatic distortions average out. For every image stretched by a foreground cluster, there are countless others only minutely altered. The large-scale picture from surveying millions of galaxies remains one of smooth, statistical uniformity. The lensing adds noise, but the signal of the large-scale structure endures. Astronomers working with the deepest fields, from Hubble, from James Webb, they talk about this challenge constantly. They're staring back to within the first billion years. The galaxies there are tiny, faint smudges, distinguishing a single small galaxy from a clump of stars inside a larger, smoother glow is an immense technical challenge. The information is incomplete, degraded by its epic journey. Interpreting these deep-field images is an exercise in statistical inference as much as direct observation. You're looking for patterns in the noise, trusting that the faint, smooth blobs you see are the assembled building blocks of the future cosmos. This fundamental information lag means our cosmic map is always out of date. It's a historical document, not a live feed. The serene universe we observe from afar is a composite portrait of different eras, all delivered by a messenger that's been subtly changed along the way. The light has been dimmed, its colors shifted, its path sometimes bent. It arrives as an echo, not a shout, and yet from this biased reporting, we've pieced together a coherent story. That forces a question about our own tools. If the messenger is so filtered, how can we possibly hope to see the universe's true, unfiltered face? The answer isn't waiting for a better messenger. It's building better interpreters. These huge maps, they need a new language, a kind of math for how things are spread out. So cosmologists, they don't just look. They calculate. They use something called the two-point correlation function. It's a statistical tool. It asks a simple thing. If you have a galaxy at some spot, what are the odds of another galaxy being a certain distance away? In a smooth, random universe, those odds would be the same everywhere, but the data says otherwise. The correlation function shows that galaxies have friends. They gather. The chance of finding a second one is much greater at short distances, inside groups and clusters. Then it falls off, but then it goes up again at the scale of the filaments. That's the math confirming the web. It measures the lumpiness, but as you go to larger and larger scales, that signal gets weaker. It fades towards zero. The clustering just dissolves into a kind of statistical sameness. The universe becomes smooth, not because there are no galaxies, but because where they are becomes random. Like raindrops on the ocean, there's another tool, the power spectrum. It does a similar analysis, but in terms of scale. It breaks the cosmic map down into a kind of symphony. The high notes, the short wavelengths, that's the small, chaotic clustering. The low, deep notes, those are the vast, smooth waves of the overall structure. And the data from surveys like Sloan shows a clear spectrum, a lot of power in the small-scale, clumpy notes, and then this steady, dominant hum of power in the largest, smoothest scales. That's the mathematical fingerprint, a universe that's both full of structure and, at its heart, uniform. It's the hard evidence that the two faces are real. Not an instrument error. For the data scientists working with all this information, petabytes of it, the feeling is deep. They talk about being cosmic cartographers. Drawing the first real atlases, their work isn't about any one galaxy. It's about the relationships between millions of them. They write algorithms to find the filaments, to measure the voids, to test against thousands of simulated universes with different starting points. The map that comes out confirms our deepest theories, from the quantum seeds to the dark energy future, but they also feel a personal disconnect. The majestic, smooth, large-scale structure they measure is invisible to us. We live in the sharp, detailed inset of that map. Our night sky is a street view, not the satellite image. That tension between the data and lived experience, it's central to cosmology now. It tells us that to see the universe as it truly is, we have to learn to see like a survey, to perceive the average, to hear that deep hum underneath all the chaotic noise. And that act of averaging, it might be hiding the next big mystery. The map comes from data, but the story gets tested in a digital forge. Inside these supercomputers, equations come to life. They become virtual universes born from code and the laws of physics. That's computational cosmology. A team might start with a cube of virtual space, billions of light years on a side. They set the starting conditions, a near perfectly smooth, hot plasma, seeded with those same tiny density ripples we see in the cosmic microwave background. Then they press start. In the silence of a server room, trillions of calculations per second turn the abstract into the tangible. Gravity acts on dark matter first, pulling it into that cosmic web of filaments and halos. Then ordinary gas flows along those dark matter rivers. It cools, it collapses, and it ignites into the first virtual stars. These aren't simple animations. They're physics engines of staggering complexity. Modern simulations like Illustris TNG or Eagle incorporate not just gravity, but gas dynamics, magnetic fields, the formation of stars within collapsing gas clouds, and the explosive feedback from supernova and black holes. The supernova explosions are crucial. They blast energy and heavy elements back into the virtual galaxy. That heats the gas, it shuts down star formation in some regions, and it triggers it in others. It's a self-regulating cycle of cosmic chaos coded into the simulation. For the scientists who build these tools, it's a new kind of laboratory. As one computational cosmologist put it, we're no longer just observers of a single universe. We've become creators of possible universes. We can run the experiment of cosmic evolution thousands of times. We tweak the fundamental parameters each time. What if dark matter was slightly warmer? What if the initial ripples were a bit larger? The simulation shows us the consequences, and the most profound validation comes when we compare the output to our real night sky. The synthetic universes produce galaxies with realistic shapes, spirals, ellipticals, irregulars. They distribute them in clusters and filaments that look eerily like the maps from the Sloan Digital Sky Survey. The virtual cosmos, grown from smooth equations, matures into a convincing replica of our own clumpy, chaotic reality. Inside the simulation, you have a God's eye view. You can zoom out to see the entire simulated box, a smooth, cloudy density field that looks like the universe's large-scale structure. Then, with a few keystrokes, you can dive into a single galaxy. The smooth cloud resolves into billions of individual star particles, swirling in chaotic spiral arms with supernova flashing like tiny fireworks. This toggle between the smooth and the chaotic is the entire cosmic story made interactive. It's like a global weather model. The simulation can predict the broad, smooth patterns of atmospheric pressure across a continent with remarkable accuracy. But within that large-scale forecast, the furious, chaotic thunderstorm that forms over a specific town is an emergent detail. You can't predict the exact lightning strike, but the conditions that make the storm possible are encoded in the smooth, large-scale data. These digital laboratories are now essential. They are the bridge between the serene equations of general relativity and the violent, beautiful mess we see through our telescopes. They show us that both faces of the cosmos are not just compatible but inevitable, two sides of the same simulated coin. Those simulations need a starting point. A first cause. To find it, you leave galaxies behind. You go to a place where scale breaks down, the quantum realm. Here, the principle of uncertainty is everything. Werner Heisenberg showed that at the most fundamental level, reality is fuzzy. You can't know a particle's position and its momentum with perfect precision. The more you pin down one, the more the other becomes this cloud of possibility. That's not a limit of our tools, it's how the universe is built. One consequence is that empty space isn't empty. The quantum vacuum is a seething foam. Virtual particle pairs, matter and antimatter, they wink into existence. They borrow energy from the vacuum for an instant, then annihilate and vanish. It's a constant dance, creation and destruction at the smallest scales. Theorists believe our smooth cosmos came from this quantum chaos. The leading idea is cosmic inflation, from physicists like Alan Guth. In the first fraction of a second, the universe went through exponential expansion. It grew by a factor of trillions upon trillions. Guth called it the ultimate free lunch. That burst of growth set the stage. During inflation, those quantum fluctuations in the vacuum didn't just vanish. The hyper-fast expansion of space grabbed them. It stretched them, it froze them in place, lifting them from the quantum foam and imprinting them as tiny ripples in the density of the early universe. Think of a calm pond at the atomic level. Its surface jitters with tiny waves from random molecular motion. Now imagine the entire pond suddenly expands to the size of an ocean in an instant. Those minuscule, chaotic jitters get stretched into vast, gentle swells across the new surface. Inflation did that to spacetime. The microscopic quantum noise became the macroscopic blueprint. The numbers are hard to grasp. A quantum fluctuation on the scale of 10 to the negative 35 meters, the Planck length, could be inflated into a seed hundreds of thousands of light years across. That's the journey from the quantum to the cosmic. It's like a nearly silent vibration on a guitar string being captured and amplified until it fills a stadium with a deep note. The original signal was chaotic, random. The final result is a smooth, coherent wave. This connection is maybe the deepest mystery in cosmology. It suggests the serene, orderly universe we see on the largest scales isn't the opposite of quantum chaos. It's its direct descendant. The smoothness is the ghost of that primordial uncertainty, magnified beyond recognition. It makes you reflect on scale. The universe doesn't have separate rules for the small and the large. It's a single, continuous reality. The frenetic dance of the quantum vacuum is linked to the majestic spin of a galaxy. It makes you wonder if chaos and order are just perspectives, dependent entirely on the lens you use to view the unbroken tapestry. The quantum realm points to a universe made of self-similar chaos, a pattern that repeats. And that suggests something. Maybe the cosmos is a fractal, a mathematical shape where the same intricate design shows up no matter where you look. A coastline looks just as rugged from the air as it does up close. A fern's leaf is a tiny copy of the whole branch. If the universe were a true fractal, then the chaos would never stop. Galaxies would form clusters, and those clusters would form larger groups, and those groups would form even bigger assemblies, on and on. There'd be no smooth background, just an infinite nesting of structure. This idea really held cosmologists for a while. Benoit Mandelbrot, who pioneered fractal geometry, proposed early models where the distribution of matter might follow that kind of boundless scaling pattern. It was elegant, profound, a cosmos with no dominant scale, where every level of zoom revealed new complexity. But the data from our galaxy surveys tells another story. The universe is self-similar, but only over a limited range. Up to about 300 million light-years, the pattern holds. Galaxy clusters look like larger clusters. Voids look like larger voids. It's like looking at a mountain range from a plane. Peak after peak, valley after valley, the rugged pattern seems to repeat. But then you go higher, you reach satellite altitude, and the whole mountain range starts to blend into the smooth, curved surface of the planet. The local fractal pattern dissolves into a larger, simpler geometry. That's exactly what happens in the cosmos. Above that critical scale, the lumpiness fades. The statistical distribution of matter becomes uniform, homogeneous. The fractal breaks. This transition isn't subtle. It's a clear, measurable feature in the data from millions of galaxy positions. The mathematics shows the clustering signal, the signature of cosmic structure, steadily weakening until it vanishes into the noise of a smooth distribution. This breakdown is one of our strongest observational proofs for large-scale smoothness. It tells us the universe isn't an endless fractal. It has a characteristic scale, a maximum size for its grainy texture. Beyond that, it becomes something else, something serene and averaged. Mandelbrot's work wasn't in vain, though. It gave us the language to describe the universe's intricate, self-similar middle scales, the very scales where we live, where complexity thrives. But its absence at the largest sizes also highlights that profound transition to homogeneity. The cosmos has two regimes governed by different rules. The chaotic, fractal-like realm of gravity-driven structure, and the smooth, geometric realms shaped by inflation and dark energy. We exist in the dynamic borderland between them, able to see both the repeating pattern and its ultimate end. This finite fractal nature leads to a final thought. If the cosmos has a maximum scale for its chaos, then the smooth backdrop isn't an illusion of distance. It's a fundamental feature of reality, as real as the stars. That finite fractal pattern, the one that dissolves into smoothness, it leads to a deeper question. A question about us. Could a universe that was chaotic at every scale ever produce beings who could look up and wonder about it? This is the anthropic angle. A philosophical lens, the Anthropic Principle in its simplest form. It suggests we observe the universe the way it is because if it were otherwise, we wouldn't be here to observe it. It's a statement about selection bias. Our existence is a filter on the kind of cosmos we can possibly inhabit. Now consider a counterfactual universe. One that truly was a perfect fractal of chaos without end. In that cosmos, the violence wouldn't be contained. Gravitational shocks from constant, large-scale collisions would ripple through space-time. Intense radiation bursts from incessant cataclysms would sterilize regions. The delicate process of planetary formation, the quieter process of biological evolution, that multi-billion-year sequence, would be impossible. No stable orbits for planets, no quiet backwaters for chemistry to experiment. Life, as we understand it, requires a stage, and that stage needs calm. It needs predictability. It needs isolation from the worst of the cosmic storm. The relative serenity we see on large scales provides exactly that. The smooth cosmic microwave background tells of a stable, cooling expansion. The regular, clockwork orbits of planets governed by Kepler and Newton, they provide the stable platforms for seasons, for climates, for the flow of time itself. The galaxy's grand rotation, that smooth average of billions of chaotic stellar paths, it creates a vast protected harbor. Our solar system orbits far from the violent galactic center in a relatively quiet spiral arm. We are, cosmically speaking, in a suburban neighborhood, peaceful enough for life to emerge and persist for billions of years. Cosmologists and philosophers like Brandon Carter, who helped formalize these ideas, and Martin Rees, who wrote on fine-tuning, they point out the remarkable balance. The initial conditions from inflation, the strength of gravity, the rate of cosmic expansion, they all seem poised within a very narrow range that allows for complexity. Tweak them slightly, and the universe either collapses too quickly into a big crunch or expands so rapidly that no structures form at all. In either case, no stars. No planets, no observers. This leads to a reflective question, almost a haunting one. Is our entire investigation, our entire map of a smooth, large-scale universe, just a product of our own necessary point of view? We can only measure the cosmos from within a pocket of order that allowed our emergence. It's like a fish born in a calm pond trying to deduce the nature of all water. It has never experienced a raging ocean current or a frozen glacier. Its reality is necessarily limited. Would any conscious observer anywhere necessarily find themselves in a similar pocket of relative calm within their universe's broader chaos? The answer seems to be yes. Consciousness may be an inherently local phenomenon, emerging in islands of stability. This doesn't diminish the reality of the smooth cosmos. Instead, it adds a profound layer of meaning to our investigation. The journey from quantum foam to galactic web isn't just a physics story. It's the necessary prelude to a universe becoming aware of itself. The two faces of the cosmos, the serene backdrop and the chaotic detail, they aren't just a curious observation. They are the complementary conditions that made our question possible in the first place. We are not just mapping the universe, we are a part of its map, a tiny notation in a vast margin that reads here, conditions allowed for reflection. And that connection forces the final practical question. Where do we, the mapmakers, go from here? The cosmos looks calm from a distance, but at the heart of galaxies, there are these supermassive black holes. They're not empty, they're these gravitational points, and when material falls into them, it creates these storms, unbelievable power. That's the active galactic nucleus. Picture a whirlpool, but it's made of gas, superheated gas, and magnetic fields, all of it spinning almost at light speed, right at the edge of the black hole. That's the accretion disk, temperatures in the millions of degrees, matter getting torn apart. It glows so brightly it can outshine the entire galaxy around it. And from that, physics does this thing. It takes some of that falling energy and focuses it into two narrow beams shooting out from the poles. These are the relativistic jets. They're made of particles accelerated to almost light speed, and they blast right through their own galaxy. They can travel for tens of thousands of light years. They act like cosmic blowtorches. They hit clouds of gas in space, heat them up, keep that gas from cooling down and forming new stars, so they regulate galaxies. They shape how galaxies grow. It's chaos, but contained chaos. The scale is hard to grasp. A single one of those jets, it has more energy than a billion supernovae. But from far away, from another galaxy cluster, you wouldn't see any of that. You'd just see a point of light, a brilliant, steady dot. That's a quasar. All the furious detail, the physics, it's completely lost. It gets smoothed out. It's like a lighthouse. From shore, miles away, you just see the beam. A calm, sweeping light on the water, part of the night. But if you're right at the base of the tower, it's totally different. The lamp is a blinding spin. The gears are roaring. The glass lens is this focused chaos, directing all that raw light into that single beam. The local reality is violent, complex. From the shore, all that machinery blends into one serene signal. The quasar is that lighthouse. We're on the distant shore. Our telescopes collect that smoothed, point-like light. And it becomes just a data point, one dot in a map of a smooth universe. There's a lesson there. The universe can have these engines of infinite violence. In incredibly small volumes, a supermassive black hole sphere of influence is tiny compared to its galaxy. That concentration is the key. The chaos is so intense because it's so contained. Its ferocity doesn't disrupt the large-scale structure. Instead, these point-like furnaces, they just add their smooth light to the cosmic background. And their focused jets silently, they shape the fate of gas on enormous scales. Scales we're still trying to map, so it adds a new layer. The universe isn't just statistically smooth. It's punctuated by islands of chaos, so brilliant that from the grandest vantage they only look like serene points of light. Those brilliant points of light, the galaxies, they're only half of it. The other half is the space between them, the voids. These are the deserts, regions of space, hundreds of millions of light years across, where galaxies are almost absent. If you were at the center of one, the view would be different. The night sky would be nearly black, maybe a few faint, distant galaxy lights, but your entire neighborhood would be defined by an overwhelming emptiness. And that's not a flaw, it's a fundamental feature. For the universe to be smooth, statistically smooth, it needs these enormous regions of near nothingness. To balance the frantic density of the galaxy clusters, they're the low notes, the long pauses between the musical phrases. Without them, the universe would be all crescendo. Just constant, overwhelming noise. Now, voids aren't perfect vacuums. They contain trace amounts of gas, extremely diffuse gas, and dark matter, always dark matter, spread in a tenuous web. But the density is so low, gravity has little to work with. Structure just failed to form here on a grand scale. These regions are the negative space. The negative space in the cosmic sculpture. Astronomers have mapped this void network for decades. Surveys like Sloan's showed they're not random bubbles. They're part of the architecture, part of the cosmic web. Picture a sea sponge, the solid material of the sponge, that's the filaments and clusters of galaxies. The dense, interconnected structure, and the holes, the empty spaces within the sponge, those are the voids. Now hold that sponge at arm's length. Your eye doesn't see each hole and each strand distinctly. It blends them into a single, solid-looking object with a uniform texture. The sponge appears smooth, and that is how the cosmos does it. That's how it achieves large-scale homogeneity. The brilliant, chaotic clusters and the deep, empty voids, they're two sides of the same statistical coin. You average them together over a volume large enough to contain both, and they produce that serene, even distribution. The view from afar, so the silence of the void isn't an absence, it's an active component, a necessary component of cosmic smoothness. It's the canvas. The canvas upon which the bright strokes of galaxies are painted, and it's vast enough that from our distant perspective, the whole painting appears continuous. Tranquil, this balance, it forces a shift in how we see emptiness. It's not a failure of creation. It's a foundational element, the foundation of its apparent peace. A sandcastle on the beach, it's a temporary thing, towers, walls, a kind of local defiance against the flat sand, but the wind and the tide, they have a plan. A one-way plan. Given time, they'll smooth every ridge, fill every moat, the whole structure gets erased. Its grains just go back into the uniform beach. And that's not just erosion, it's a law, the second law of thermodynamics. It says entropy, that's a measure of disorder, of randomness. It always increases in a closed system. And the universe is the ultimate closed system. So entropy always increases, and that increase often leads to a kind of maximum uniformity. Think of cream in black coffee. At first, the cream is a distinct cloud, a pocket of local order, but leave it, the two liquids mix, they reach equilibrium, a smooth, uniform beige cup. No interesting gradients left, no energy you can usefully extract. That's maximum entropy, and physicists argue that's the direction our entire cosmos is headed. Irrevocably, this view adds an arrow to time. It gives the cosmic story a direction, from lower entropy in the past to higher entropy in the future. The early universe, for all its hot density, was in a remarkably low entropy state. How do we know? Because it was smooth, a uniform soup. That might sound like disorder, but in thermodynamic terms, with gravity in the picture, uniformity is a very specific, very unlikely arrangement. Gravity wants to clump things, so a smooth distribution of matter is an extremely ordered starting point. It's low probability, like having all the air molecules in your room suddenly gather in one corner. That's low entropy. What we see happening is the natural tendency. That smooth gas clumps into stars and galaxies, and that increases the overall gravitational entropy of the universe. So, paradoxically, the formation of all the beautiful structures we see, the galaxies, stars, planets, that's actually the universe moving toward a state of higher disorder. It's the cream mixing into the coffee, but in a gravitational sense. The local creation of order, like a star forming, it always comes at a greater global cost. A star is an engine of order. It fuses hydrogen into helium in a stable process, but to do that, it has to radiate vast amounts of heat and light out into the cold void. That radiation is high entropy energy, spread thinly, uniformly across the cosmos. The star's local order is paid for by increasing the disorder of the universe as a whole. The sandcastle is built, but only by scattering more sand across the beach, and this leads to the most long-term forecast, the heat death of the universe. If current acceleration continues, the story ends not with a bang, but with a slow, cold sigh. All nuclear fuel in all stars will eventually be exhausted. Black holes will evaporate over incomprehensible eons. All matter may decay into its most stable particles. The universe will approach thermodynamic equilibrium, a state where energy is perfectly, evenly distributed, a final, ultimate smoothness, a vast, dark, uniform sea near absolute zero, no gradients, no structures. No change, that's maximum entropy. The beach, after the last grain of the last sandcastle has been scattered, so we live in a privileged and fleeting moment. A cosmic spring nestled between two winters of smoothness. We emerged after the first smoothness of the Big Bang, and we are witnessing the glorious, chaotic summer of structure formation, which is the universe's journey toward its final, cold smoothness. Our entire epoch of galaxies and life exists because entropy is increasing, but hasn't yet reached its maximum. We are the intricate swirls in the mixing cream, beautiful and temporary patterns on the way to equilibrium. This thermodynamic view, it doesn't diminish our reality. It frames it. It tells us that the chaos we see up close, the forces building complexity, they're part of a grand, one-way flow toward an eventual, profound calm. The universe has a trajectory, and we are here for the most interesting part of the ride. A telescope is a window, but any window has its limits. Even the best ones impose a fundamental limit on what we can see. That's angular resolution, the smallest angle between 2 points of light that the telescope can tell apart. For Hubble, that's about 0.05 arcseconds. To picture that, it's like seeing two fireflies 6 feet apart from 10,000 miles away. It's astonishing precision, but it's not infinite. When galaxies or star clusters are farther away than that scale, their light merges. What should be a swarm of individual points gets blended by the optics into a single, smooth glow. The tools are painting over the fine details. This smoothing happens for two main reasons. First, there's the diffraction limit. It comes from the wave nature of light. As light passes through the telescope's aperture, it bends. It creates a tiny, blurred disk for each point source, an airy pattern. Two stars closer together than the width of this disk appear as one. A larger mirror makes a smaller disk. That's why we build giants like the James Webb Space Telescope. But even Webb has its limit. For ground-based telescopes, a second filter gets added: atmospheric seeing. The Earth's atmosphere is a churning ocean of air. It distorts incoming starlight, makes it twinkle and blur. This can reduce effective resolution by a factor of 10 or more. Sharp pinpoints become fuzzy blobs. From the ground, the universe looks smoother, more serene, because our own atmosphere is blurring the chaotic truth. To fight this, astronomers developed adaptive optics. It uses a laser to create an artificial guide star high in the atmosphere. Sensors measure how that laser beacon is distorted, and a computer deforms the telescope's mirror hundreds of times per second to cancel out the turbulence in real time. The results are transformative. Images of the galactic center from telescopes like Keck show individual stars whirling in frantic orbits around the supermassive black hole. A chaos that was once just a smooth, bright smear. The technology peels back the atmospheric veil, but it can only do so much for the most distant objects. When we point telescopes at the earliest galaxies, at the edge of the observable universe, we're often looking at an unresolved smear, a single pixel of light that contains the combined glow of billions of stars across thousands of light years. We infer the chaos from the properties of that light, but we can't see it directly. It's the ultimate pixelation. Think of a digital photograph. From a normal distance, it looks smooth, a face, a landscape. You zoom in closer and closer, and the illusion breaks. The smooth gradients resolve into a grid of blocky squares of pure color. There's no finer detail. That's the limit of the image resolution. Our telescopes, even in space, face the same constraint. The cosmos has detail down to the quantum scale, but our windows only provide a certain number of pixels. For the most distant reaches, we're viewing the universe at its lowest resolution setting. The serene picture we compile is partly a product of our instrument's finite eyesight. To see the true, chaotic texture, we have to build bigger mirrors and sharper optics, and learn to read the stories hidden within the smooth, pixelated light itself. The ancient Greeks looked up at the stars. They saw heroes and beasts. They connected those bright, random points into figures: Orion the hunter, Taurus the bull. That act of constellation making it was a human instinct, imposing a narrative, a smooth, comprehensible story onto a chaotic scatter of stars. The sky became a serene tapestry. A map of the gods' domain, rotating with clockwork harmony. That was the smooth cosmos, the one we perceive, but woven into those same myths was an acknowledgement. The Greeks also told of Phaethon. He lost control of the sun chariot and scorched the earth. They saw comets not as predictable planets, but as terrifying omens. Hairy stars that disrupted the divine order. Norse cosmology envisioned the cosmos as a great tree, Yggdrasil, a stable structure, but it was constantly under threat. From chaotic forces like the serpent Nidhogg gnawing at its roots, all leading to a final chaotic battle. Ragnarok, Aboriginal Australian traditions, some of the oldest star lore on Earth. They often see the sky as a landscape. A smooth, storied territory, but within it they track the variable stars, stars whose changing brightness tells stories, stories of conflict, love, betrayal among the ancestral beings. These aren't primitive mistakes, they're sophisticated cultural responses to the same duality we now measure with telescopes. The serene, patterned sky gave a calendar for planting, a compass for navigation, a testament to cosmic order. The chaotic events, comets, eclipses, nova, they were reminders of a capricious universe that couldn't be fully tamed by story. Historians of science see this universal drive. The human mind is a pattern-seeking engine. We find faces in clouds, animals in star clusters, causes in random events. This cognitive trait is foundational to both mythology and science. It's what led ancient priests to chart planetary cycles and modern cosmologists to map the cosmic web. The quest is the same: to find the signal in the noise, to distinguish the enduring pattern from the temporary tempest. Our scientific maps of dark matter, of inflationary theory, they're the direct descendants of those first star maps drawn in clay. They're more precise, more powerful, but they serve the same deep need: to reconcile the tranquil heavens we see from a quiet hilltop with the terrifying forces we know must reside within them. This cultural lens shows us something. The smooth versus chaotic cosmos isn't just a physical reality, it's a perceptual reality, a psychological one. Etched into human culture long before the first telescope, our modern equations are a new language for an ancient story, one that still bridges our wonder with our desire to understand. Our clearing of smoothness and chaos, it might not be the only one. There's this idea, the Multiverse Hypothesis. It's one of cosmology's more radical proposals. It says what we call the universe is just one region, one bubble, in a far vaster and older meta-universe, a cosmos of cosmoses. In that picture, the inflation that smoothed our early universe never really stopped. It keeps going eternally in a background sea of space-time. New bubble universes nucleate constantly, like bubbles forming in boiling water. Each bubble could have different fundamental constants. Different gravity, different electron masses, different outcomes. In some, the forces might be so weak matter never clumps. The whole universe stays a perfectly smooth, thin haze. No stars, no galaxies, just a silent, uniform fog. In others, the forces are so strong collapse happens instantly. Matter might clump into black holes immediately. A universe of relentless, grinding turbulence. No stable structures. Our universe occupies a narrow middle ground, a Goldilocks zone, where the constants allow both the large-scale smoothness from inflation and the gravitational instability to build complex, chaotic structures within it. We're in a bubble where the balance is just right for galaxies, for life. Physicists like Max Tegmark have categorized levels of multiverse. The level from eternal inflation, that's a compelling one to many theorists. It connects to another framework, string theory. String theory suggests our fundamental constants might not be fundamental laws. They could be accidental outcomes, determined by how extra dimensions of space are curled up, a configuration in a vast landscape of possibilities. Our universe's specific settings, this smooth, chaotic mix, might be a single point in an almost infinite landscape. The mechanism to jump between points is quantum tunneling, the same process that lets particles penetrate barriers. In this grand view, our entire universe could have tunneled into existence from some other state. This perspective is humbling. It frames our cosmic conditions as possibly accidental, not designed, stumbled upon. The fact we find ourselves in a universe with this beautiful tension, serene backdrop, vibrant detail, might be a cosmic coincidence. Yet it makes that duality seem even more precious. It's not the default state of all reality. It's a special, perhaps rare arrangement, one that allows observers to arise and notice it. Picture an endless forest, dark and impenetrable. Within it are clearings. Most are either too small, just a patch of dirt, or overgrown with such tangled thickets no light gets through. But one clearing, by chance, is just the right size. It has open fields that let in the sun, and stands of trees that provide shelter and complexity. That's our universe. The open field is the large-scale smoothness. The isotropic expanse that lets light travel provides a stable stage. The stands of trees are the galaxies, the stellar nurseries, the local chaos where complexity is forged. We find ourselves in this particular clearing, able to appreciate both the sky and the woods. The multiverse idea expands the mystery to an infinite canvas. It asks if the smooth, chaotic duality we've mapped is not a universal truth, but a local bylaw, one chapter in a library of universes whose full collection we may never read. It turns our investigation inward, pondering not just how our cosmos works, but why this one, with its fleeting balance, is ours to witness at all. Spacetime can carry a tremor. A ripple, these are gravitational waves. Einstein predicted them a century ago. They're wrinkles in the geometry of the cosmos, and they only come from the most chaotic events. Two black holes, each millions of times the mass of our sun, spiraling together and merging, or two neutron stars colliding. At the source, it's an apocalypse. Space and time are distorted. In a fraction of a second, energy equal to several suns is converted into pure gravitational radiation. The violence is absolute. But by the time those ripples travel billions of light years to reach us, they're incredibly faint. The signal is a smooth, sinusoidal whisper, and it's buried in a sea of noise. The ground itself trembles, from trucks, from ocean waves, from tiny seismic shifts. Finding the cosmic signal is like trying to hear a single violin note from another city while standing in a roaring stadium. That was the challenge. It took decades to solve. The solution was LIGO, the Laser Interferometer Gravitational Wave Observatory. Its design is a masterpiece of precision. Two arms 4 kilometers long, arranged in an L. A laser beam is split, sent down each arm, reflected back and recombined. In perfect calm, the light waves cancel out. You get darkness, but when a gravitational wave passes through, it does something subtle. It stretches space in one direction and compresses it in the perpendicular direction. For a fraction of a second, one arm becomes infinitesimally longer, the other becomes shorter. The laser light in one arm travels a slightly different distance. So the waves no longer cancel perfectly. A flicker of light appears in the detector. That flicker is the signal. The first direct detection in 2015 was a triumph of hearing. It was the sound of two black holes over 1 billion light years away becoming one. Think of a stone dropped into a still pond. The initial splash is chaotic. Water erupts, droplets scatter, but what travels across the pond's surface aren't the splashes. They're clean, expanding circles, ordered ripples. They carry the energy of the chaos, but in a smoothed, simplified form. Gravitational waves are those ripples on the pond of spacetime. The chaotic splash is the merger. The clean circles are the waves we detect, and these ripples in spacetime barely interact with matter. They pass through planets and stars almost as if they weren't there, so they preserve, in their waveform, a pristine record of the cataclysm that created them. By reading that smooth, sinusoidal signal, physicists can decode the masses of the colliding objects, their spins, even the location of the event in the sky. It's a direct messenger from the heart of chaos, traveling untouched across the cosmological background. This shows a new layer to a cosmic duality. The most violent events don't just create local disorder. They imprint that disorder onto the smooth fabric of spacetime itself. They send out a signature that, over vast distances, becomes a serene mathematical curve. The chaos isn't erased, it's encoded, translated into a language of pure geometry. A language we can only understand by listening to the quietest tremors in the universe. You see this gravitational wave, it's a perfect, smooth curve on a graph, and then you think about the collision that made it, an unimaginable cataclysm. So which one is more real, the serene mathematical signal or the violent event it points to? That question, it forces you to confront the nature of reality. Because the cosmos has two faces. Is the smooth universe the true one, or is the chaotic universe the truth? the answer from modern physics is surprising. Both are equally real. They're not competing truths, they're complementary descriptions. Each one is valid, each one is complete, but within its own domain of scale. There's a concept for this, emergence, where complex, novel properties arise from simpler interactions, but they can't be reduced to them. Think of a living cell. At one scale, it's a bustling metropolis, organelles, chemical pathways, electrical signals, a chaotic, intricate dance. Then you zoom out to the tissue level. And that cellular chaos gives rise to something else, a smooth, uniform sheet of skin. The property of smoothness, it emerges from the underlying frenzy. The skin is real, the cellular chaos is also real. One doesn't negate the other. They're different levels of description of the same system, and the universe operates on this principle. Across all scales, the serene, homogeneous cosmos that obeys general relativity on large scales, that's an emergent reality. It arises from the statistical averaging of trillions upon trillions of chaotic quantum-scale events. Philosophers of science have debated this tension between reductionism and holism. Reductionism seeks to explain everything by breaking it down to the smallest parts, the chaotic particle-level view. Holism argues the whole has properties its parts do not. The smooth, large-scale view, the physicist P. W. Bridgman noted something. A concept is synonymous with the set of operations you use to measure it. The operations to measure the smooth, cosmic microwave background. They're utterly different from the ones you use to measure a supernova's explosion. You're measuring two different aspects of the same cosmos. Each measurement reveals a true facet. This leads to a profound question, almost unsettling. Does reality have a preferred scale? Is there a fundamental level where things are finally, truly real? Our intuition screams yes. We feel the solidity of a table. But quantum physics tells us that solid table is over 99.999% empty space, a whirlwind of quantum fields and fleeting particles. The solidity we experience, it's an emergent property of the electromagnetic forces between those particles. It's no less real for being emergent. It's the reality at our human scale. So perhaps the universe itself has no single privileged scale of truth. What we call reality is a spectrum of valid descriptions. Each layer, from the quantum foam to the galactic supercluster, has its own laws, its own phenomena, its own kind of truth. Our scientific understanding, then, isn't a single, perfect model. It's a tapestry of scale-dependent models. Newtonian mechanics works perfectly for sending a rocket to the moon. It breaks down near a black hole where general relativity takes over, and both fail to describe the quantum birth of the universe. They're not failures, they're different maps for different territories. The smooth cosmological model and the chaotic astrophysical model, they're two such maps. One for the continent, one for the city streets. To ask which map is the true territory is to misunderstand the purpose of a map. This lens, it transforms the cosmic contradiction. It's no longer a puzzle to be solved, it's a feature to be understood. The universe is not either smooth or chaotic. It's a multi-layered reality, a symphony with movements written for different instruments. The deep, low hum of dark energy, the rhythmic chords of galactic rotation, the staccato bursts of stellar explosions, all are playing at once. Our perception and our science can only listen to one movement at a time. But the full majesty of the cosmos requires us to hold both, the serene melody and the chaotic harmony, in our minds at once. This isn't just physics. It's a metaphysical insight into the layered nature of existence itself. This cosmic duality isn't just a philosophical idea. It's how we actually navigate our place in space. Every satellite we put up there, every signal we send to a rover, it all works within this reality of smooth fields and local storms. Our whole approach to space is built on that. We depend on the predictable, smooth curve of Earth's gravity to calculate orbits for the International Space Station, for GPS satellites. That large-scale order is our highway. But on that highway, we have to dodge things. We navigate the chaotic debris of micrometeoroids, the turbulent gusts of solar wind that can scramble communications, that can endanger astronauts. That's the local chaos. It's a space weather forecast, and it's as vital as the orbital map. This understanding shapes how we search for life. Astronomers hunting for exoplanets often use the transit method. They watch for a tiny, regular dip in a star's light as a planet passes in front. That technique assumes a stable, smooth clockwork. But to read that faint signal, scientists first have to filter out the star's own chaotic activity. Its flares, its sunspots, the churning of its plasma. They're separating the serene planetary signal from the stellar noise. It's directly applying that idea, distinguishing cosmic smoothness from local chaos. The drive to map this duality fuels our biggest tools. Take the Vera C. Rubin Observatory being built in Chile. Its mission is the legacy survey of space and time, a 10-year cinematic map of the sky. It won't take a single, smooth picture. It will capture chaos in motion. It will track asteroids whizzing through our solar system, watch distant stars flare, map the subtle gravitational lensing from dark matter. Its data stream will be a turbulent river of local events, but the grand goal is to use that river of chaos to infer the smooth, large-scale structure of the cosmos, the nature of dark energy. The telescope itself is a bridge between the two. The computational challenge is staggering. Processing this avalanche requires algorithms that can spot rare, chaotic events while also performing statistical analyses on billions of objects to reveal the underlying smooth patterns. It pushes the frontiers of artificial intelligence, and the technology developed to pass the cosmic duality finds uses closer to home in medical imaging, climate modeling, network security. The quest to understand the universe's two faces becomes an engine for innovation here. A sailor on a long voyage uses two kinds of knowledge: the star chart, the map of ocean currents, the large-scale, smooth guides that set the course. And then the daily weather report, the lookout for rogue waves, the chaotic, local conditions that determine the safety of each day's journey. Neither map is enough alone. Our journey into the cosmos works on the same principle. The cosmological models, the maps of galactic distribution, those are our star charts. The real-time monitoring of radiation belts, tracking orbital debris, forecasting solar storms, that's our weather report. Mastering both is what lets us move from just observing the stars to truly sailing among them. Our future as a spacefaring species depends on reading the universe in both its voices, the serene hum of the background and the vibrant, chaotic song of the foreground. Every map has an edge. Every theory has a horizon. We've mapped so much, but the cosmos still has these deep mysteries right at its foundation. The forces that create this balance between smooth and chaotic dark energy, dark matter, the quantum beginning, they're still deeply unknown. Their true nature is the next frontier, and it could reshape our whole understanding of the cosmic duality. Take dark energy. We measure its effect, the accelerating expansion. It acts as the ultimate cosmic homogenizer, but we have no idea what it actually is. Is it a constant energy woven into space itself, like Einstein once proposed? Or is it a dynamic field that could change over time, maybe even reverse its effect in the far future? The answer determines the ultimate fate of smoothness. If dark energy strengthens, it could lead to a big rip, tearing apart all structure, imposing a final, absolute smoothness. If it weakens, gravity might regain dominance, potentially collapsing the universe back into a hot, dense state. We just don't know. As cosmologist Catherine Fries has pointed out, dark energy is arguably the deepest mystery in physics today. Its resolution tells us whether the serene backdrop we see is a permanent stage or just a temporary phase in a much more dramatic cycle. Then there's dark matter. We map its smooth gravitational scaffolding, but we've never directly detected a single particle of it. Is it a sea of undiscovered heavy particles, like most physicists suspect? Or could it be something stranger, like primordial black holes formed in the universe's first second? The answer matters for the story of structure. Different types of dark matter, cold, warm, or fuzzy, would clump on different scales, changing the detailed blueprint from which galaxies formed. The smooth distribution we see on the larger scales is a clue. But it's not a solved equation yet. And before both of these, there's the quantum origin. Inflation explains the large-scale smoothness and the seeds of structure. But what triggered it? What was the universe like before inflation, if before even has meaning? This pushes us into quantum gravity, where our two most successful theories, general relativity for the smooth cosmos and quantum mechanics for the chaotic small scale, they collide. They contradict each other. At the Planck scale, distances so tiny they defy imagination. Spacetime itself is predicted to become a chaotic foam, a seething, probabilistic froth where here and now break down. Does this fundamental foaminess leave any trace on the large, smooth universe we see? Some theories suggest it might, imprinting subtle patterns in the cosmic microwave background, or in the polarization of light across the universe. We're looking, but so far, the serene face of the cosmos shows no definitive scars from its tumultuous birth. These unknowns force open these questions. Is our observable universe, for all its vastness, just one homogeneous patch in a much larger, uneven meta-universe? Could there be structures so immense they span beyond our cosmic horizon? Making a mockery of our assumption of large-scale smoothness, we may never know. Light from those regions can never reach us. And perhaps most hauntingly, are smoothness and chaos truly fundamental? Or are they, like hot and cold, just human perceptions of a reality that's something else entirely? Leading researchers like Nobel laureate Adam Rees, who helped discover dark energy, they often speak of this not with frustration, but with exhilaration. The biggest unsolved problems, he notes, aren't dead ends. They're signposts pointing to a deeper layer of reality, waiting to be uncovered. Every answer we've found about the cosmos has revealed a deeper, more beautiful question. This isn't a failure of science, it's its very engine. The universe's two faces, the serene and the chaotic. They're not a puzzle we'll one day solve and file away. They're a dynamic conversation, a dialogue between our tools, our minds, and the profound, layered reality we're a part of. The mystery is alive, and our map for all its detail is still being drawn. The universe isn't one thing or the other, it's both at the same time, a single reality that just looks different depending on where you stand. The calm cosmos and the violent one aren't fighting. They come from the same rules, just seen through different lenses, through scale, through interaction. The averaging over huge volumes, gravity's constant pull, dark energy's push, the limits of light and our tools, these aren't separate. They're threads in one fabric. They work together to build the reality we see. From the quantum scale to the superclusters, each layer has its own description. Its own emergent truth. That's how the paradox resolves. The cosmos isn't a contradiction. It's a coherent system. Its beauty is in that layered complexity. Think of a symphony heard from the balcony. You experience a smooth, harmonious blend. A single piece of music washing over you. That's the large-scale universe, the serene background, the hum of dark energy, the smooth cosmic web. Now walk down to the orchestra pit. Your perspective shifts. You see the chaotic motion of each musician, the violinist's frantic bowing, the percussionist's strike, the flutist's breath. You hear distinct, sometimes clashing, notes before they merge. That's the universe up close, the supernova flash, the black hole's disk, the turbulent stellar nursery. Both experiences are true, both are needed to grasp the whole. The symphony can't exist without each musician's effort, and that effort only finds meaning in the combined harmony. The conductor here is the physical laws: gravity, quantum mechanics, thermodynamics orchestrating the parts into one evolving composition. This view changes the questions. We stop asking which picture is real. We ask how the pictures connect. How does quantum jitter become a galaxy? How does a star's death enrich the cosmos? The answers are in the bridges between scales, in gravitational instability amplifying tiny seeds, in thermodynamics allowing local order at the cost of global entropy. Our scientific models aren't failures because we need different ones for stars and for the cosmos. They're triumphs of scale-appropriate understanding. Newton's laws perfectly describe an apple's fall and the moon's orbit in our chaotic solar system. Einstein's equations describe the smooth curvature of the cosmos on the grand stage. Each model is true for its domain. Together they map the journey from the pit to the balcony. So when you look at a deep field image from the James Webb Telescope, see both faces. See the countless chaotic points of light, each a galaxy of billions of stars, each star a possible crucible of planets. Then soften your gaze. See the overall pattern, the clustering, the vast dark voids. See the smooth statistical distribution that speaks of inflation and dark energy. One isn't a trick, the other isn't an illusion. They are the same universe speaking in two voices. A dialogue between the individual and the collective, the temporary and the enduring, the chaotic note and the serene chord. Our privilege as observers is to listen to both and to start understanding the single composition they create. We end where we started, just looking up. We followed the light from its first murmur in the cosmic microwave background, across the growing filaments of the dark matter web, into the violent hearts of stellar nurseries and the quiet depths of intergalactic voids. We saw how scale and gravity and statistics and the limits of our own perception work together to show us a universe with two faces. This isn't a flaw, it's the most elegant feature. The serene backdrop and the chaotic detail, they aren't in conflict. They're in conversation, a dialogue written into the laws of physics, from the quantum uncertainty that seeded everything to the dark energy that will one day smooth it all away. So next time you stand under a clear, dark sky and see that tranquil blanket of stars, remember what you're seeing. You're not looking at a static picture. You're witnessing a grand statistical average, a moment of profound peace. That's the sum of a trillion ongoing cataclysms. Each point of light is a story. Gravitational collapse, nuclear fusion, explosive death. Each dark patch between them is a vast desert, a necessary counterweight in the cosmic balance. Together they create an illusion, stillness from a storm. That knowledge doesn't diminish the beauty, it deepens it. It connects your gaze directly to the forging of elements in ancient stars, to the quantum tremors of the first instant, to the invisible scaffolding of dark matter, holding the entire scene in place. You are part of this tapestry. A temporary pattern of order emerging from the chaos, granted the fleeting privilege to look back and to wonder. Let that feeling linger. Let it fuel your curiosity for the mysteries that remain.